this mini lecture, we're still in the area of kinematics of a particle, but specifically, we're going to look at rectilinear kinematics, erratic motion. So after this mini lecture, what we're going to be able to do is determine the position, determine velocity, and determine acceleration of a particle just using their graphs. So in many experiments, a velocity versus position, that's V versus S, velocity versus position, V versus S, profile is obtained. So if we have a VS graph for this tanker, this truck, this tractor trailer tanker truck, a question that would come up that we're going to understand how to do soon is how can we determine its acceleration at position S equaling 1,500 feet? Okay. Also, the velocity of a car. Here we have the velocity of a car on the right. So the velocity of a car is recorded from an experiment. So let's say the car starts from rest and then travels along a straight track. All right, so if we now know the VT, velocity time, the VT plot, our question would then probably be, how can we determine the distance the car traveled during the time interval where t is between 0 and 30, or let's say t is between 15 and 25 seconds, right? We're going to be able to answer things like that given these plots. Okay, so now let's take a look at erratic motion. Erratic motion. So graphing provides a really good way to actually handle complex motions that will be really difficult to describe with just formulas. And then graphs, they also give us this visual description of motion, and then they reinforce the calculus concepts of differentiation and integration as used in a course like dynamics. All right, so the approach builds on the facts that slope and differentiation are linked, and that integration can be thought of as finding the area under the curve, right? And we've all learned this in our calculus sequence courses. All right, let's take a look at the ST graph. Okay, so plots of position versus time can be used to find velocity versus time curves. Plots of position versus time can be used to find velocity versus time curves. So finding the slope of the tangent line to the motion curve at any point is the velocity at that point. So I'll say it again. Finding the slope of the tangent of the line tangent to the motion curve at any point is the velocity at that point, right? Or v is equal to ds dt is what I'm saying. Therefore, the vt graph, the velocity time graph, can be constructed by finding the slope at various points along the st graph. This velocity time graph can be constructed by finding the slope at various points along the st graph. All right, looking at the VT graph. So plots of velocity versus time. Velocity versus time. Plots of velocity versus time can be used to find acceleration versus time, right? We can find acceleration versus time curves given velocity versus time. So finding the slope of the line tangent to the velocity curve at any point is the acceleration. I'll say it again. Finding the slope of the line tangent to the velocity curve at any point is the acceleration at that point, right? Or we could say simply A is equal to dv dt, derivative of velocity with respect to time. So therefore the acceleration versus time, or the AT graph, this can be constructed by finding the slope at various points along the VT graph to the right, to the left. All right, and then also the distance moved, which we know as the displacement. So the displacement of the particle is the area under the VT, the velocity time graph, during time delta t. I'll say that one more time as well. The distance moved, which is the displacement of the particle, is the area under the VT graph during time delta t. And we look at a t graph. All right, so here now we're given the acceleration versus time, or what we can call the AT curve, right? Given the acceleration versus time, or AT curve, the change in velocity, which is delta v, during a time period is the area under the AT curve. All right, so given the acceleration versus time, or AT curve, the change in velocity, which is delta v during a time period, is that area which is under the AT curve. So then we can construct a VT curve, a VT graph, from an AT graph if we know the initial velocity of the particle. And we have the AS graph. Okay. All right, with the AS graph, a more complex case is presented by the acceleration versus position, or what's known as the AS graph. The area under the AS curve represents the change in velocity. The area under the curve represents the change in velocity, right? And this is for the AS curve. The area under the AS curve represents the change in velocity. So if we recall, the integral of A ds is equal to the integral of V dV. All right, so we'll have 1/2 of V sub 1 squared minus V sub O squared is equal to the integral, as we go from S1 to S2, of A ds, right? This is the area, and this is equal to the area under the AS graph. It's equal to the area under the AS graph. So this equation can be solved for V sub 1, right? We can solve for V sub 1. And then allowing you to solve for the velocity at a point. So then by doing this repeatedly, you can create a plot of velocity velocity versus distance. So we could have a plot of velocity versus distance. So there's S and there's V. And we'll have S1 there VO, V1, then from VO, have it looking like that, right? So again, the equation, if we have it, the equation can be solved for V sub 1, allowing you to solve for the velocity at a point, right? By doing this repeatedly, then we can create a plot of velocity versus distance that I've just drawn. Okay, and then we have the VS graph. The VS graph. So another complex case is presented by the velocity versus distance, VS graph, the velocity versus distance graph. So by reading the velocity V at a point on the curve and then multiplying it by the slope of the curve, right, dV ds, at this same point, then we can obtain the acceleration at that point. So if you recall, the formula A is equal to V dV ds, right? Recall that. Thus, we can obtain an AS plot, right? An AS plot from the VS curve. Okay, so let's look at this example. So here, what are we given? We're given that the VT, the velocity time graph for a dragster race car moving along a straight road. All right, then what are they asking? They're saying to find the AT, acceleration time graph, and ST graph over the time interval that is shown. Okay, let's see. What is going to be the plan of attack for this problem, given what we have? Okay, so here's our solution, how we're going to work through this. Excuse me. So the AT graph, that is going to be constructed by finding the slope of the VT graph at key points, right? What are those? So again, our solution is the AT graph is going to be constructed by finding the slope of the VT graph at key points. So what are those points? So when T is between 0 and 5 seconds. So V between 0 and 5 is ds dt. So that's going to be d 30 t over dt, right? So then that gets us the derivative of 30t is just going to get us 30, and that's meters per second squared. All right, when t is between 5 and 15 seconds, so v 5 to 15, okay, that's going to get us, again, we're using ds dt, d substituting in for s, we have negative 15t plus 225, okay, over dt. Now the derivative of negative 15t plus 225, we're just going to use a addition subtraction rule for differentiation. It's going to give us negative 15. We can just differentiate each term. 15 and then this is going to be meters per second squared. All right, and then I can show the AT graph on the right. All right, so now we can integrate the VT graph. Now we're going to integrate VT graph. All right, and this is so that we can build the ST graph. All right, so when t is between 0 and 5 seconds, s is equal to the integral of v dt, and that's going to be 15t squared. And we're going from 0 to t, 0 to t. And this is going to give us, according to our calculus, 15t squared. All right, and then we can also say when t is between 0 and 15 seconds. So we'll have s minus 15 times 5 squared. All right, what's that? That's going to be integral of v dt is equal to negative 15 is 1/2 t squared plus 225t, and this is from 5 to t. All right, and then based on that, we should get the following. And there we have it. And you see how we moved into our solution based on using our calculus with the different graphs. And just as a side note, make sure you're up to speed with the calculus, right? The integration and the inputting the upper limits and the lower limits so that you are able to get what we have in red with the negative 7.5 t squared plus 225t minus the 562.5, right? That upper limit minus the lower limit being plugged in yields this. All right?